Hi, I want to address two of the questions, or perhaps two ways of framing the same question, that often come up in discussions about CHERI. CHERI lets us retrofit strong deterministic, non-bypassable memory safety to languages like C and C++. So why do we need safe languages if we have CHERI? Or, to put the question the other way, if we have safe languages, and Microsoft's investing a lot in languages like TypeScript, C#, and Rust, then why do we need CHERI? To answer these questions, I want to explore a bit the guarantees that you get from safe languages. The difference between a safe language, such as C#, and a safe implementation of a language, such as CHERI C, is largely a matter of reliability. CHERI C gives us very strong confidentiality and integrity guarantees, but it doesn't give us the same availability guarantees. All three of these are important for critical infrastructure. So what do I mean by these different guarantees? Existing C and C++ implementations are in a very bad position. Programming errors can give an attacker full control of the running process, even though we deploy a lot of mitigations today that make this a lot more work than it was 20 years ago. CHERI C and C++, in contrast, are in a really great position for confidentiality and integrity. A lot of memory safety errors cause the program to stop. That's not wonderful for availability, though. Safe languages, in contrast, guarantee that these errors are either impossible to create in the first place, or that there are in-language mechanisms for detecting and gracefully recovering from them. So since safe languages are obviously better, the solution seems pretty obvious. We should just rewrite everything in our favorite safe language. If we want to rewrite all of the existing C and C++ code, how much effort is that going to be? OpenHub reports about 13 billion lines of C and C++ code, just counting public open source repositories. So that's not including any in-house proprietary code. So that's a very low estimate of the total amount of unsafe language code in the world. And how much would it cost to rewrite all of that code in safe languages? Well, assuming a fairly low estimate of the cost to rewrite in the order of $10 to $100 per line of code, and assuming that someone actually understands everything that's going on in the existing code bases and is able to rewrite it, then we're talking somewhere on the order of hundreds of billions to trillions of dollars to rewrite all of this code. Now that's a huge amount of money, even without counting the opportunity cost from making developers stop solving new problems until they've rewritten everything that exists today. And if that wasn't bad enough, the problem's actually even worse than that, because a lot of this unsafe code is implementing things that you simply couldn't implement in a type-safe language, not least the core parts of those type-safe languages themselves. The code that fits this description includes some of the most security-critical code of all, the code that everything else depends on as part of its trusted computing base. So if we can't rewrite all of the existing code, can we at the very least stop adding to the amount of unsafe code in the world? I'm not optimistic that we can even get to that point for a long time. 20 years ago, there were much better alternatives than COBOL for business logic, yet a very quick job search shows that companies are still today hiring people to write new COBOL code. Even if we have a really strong desire to abandon unsafe languages across the entire industry, I don't think we're going to get to the point of no new code being written in languages like C and C++ for a very long time. Can we at the very least rewrite the most important parts of our code, the parts that an attacker has the most chance of being able to control? Well, when we think about rewriting parts of a program in a safe language, we have this two worlds mental model. A safe world for the safe new code, which communicates with the unsafe world via some well-defined interfaces. Unfortunately, in the real world, all of that safe code is inside the unsafe world, which means any memory safety bugs in the unsafe code have the potential to violate all of the invariants that the safe language code depends on. So far, this seems like a pretty bleak picture. We don't get the security benefits from safe languages until we've rewritten absolutely everything, and yet rewriting everything isn't economically viable. We can use CHERI with existing code, but if we do so, we don't get the reliability benefits that we get from rewriting in a safe language. But what happens if we have both? What happens if we have CHERI and we have safe languages? CHERI sandboxes provide us with a mechanism that we can use to isolate individual instances of unsafe libraries for use in a safe language program. If an individual library instance encounters a memory safety error, then we can report this to the safe language, which can then gracefully recover, knowing that the error didn't corrupt any of the state in the safe world. Before I talk about what the language needs to do, I want to share one of the key lessons that I've learned from the CHERI project, which is directly related to this problem. Complete isolation is very easy. The problem becomes a lot more difficult only when you want to share data or communicate between isolated components. CHERI was designed as much for sharing as it was for isolation, to enable you to share individual objects between compartments with a variety of different policies. Imagine a system with fine-grained sharing between safe code and unsafe but sandboxed code, like the one in this picture, with pointers flowing between any set of objects. Following pointers within the safe world is safe by definition. The language is there to provide you with strong type safety guarantees. Similarly, following pointers inside the unsafe world is fine, as long as they continue to point back into the same unsafe world. CHERI allows you to enforce this very cheaply in one of two ways. You can use a single capability for an entire unsafe world, which could contain unmodified binaries, or you can recompile the unsafe code to use object granularity capabilities for all pointers. There are 2 pointers in this diagram that we need to treat as special. When following a pointer from the safe world into the sandbox, the language needs to understand that it's now accessing unsafe objects, and so it must assume that the unsafe code is able to tamper with any of these objects. In the opposite direction, if a pointer goes from the unsafe world back into the safe world, then the safe language must ensure that it hasn't been tampered with, and that the object that it points to remains valid. CHERI's sealing mechanism provides a language implementation with some tools that it can use to enforce these guarantees. A pointer to a safe object can be sealed before being passed into the unsafe world, and it's then protected by the hardware against tampering. CHERI provides tools for a safe language to implement these abstractions, but it isn't sufficient by itself. You also need the safe language's type system to cooperate. Consider this really trivial example of a simple field assignment in any object-oriented language. If we want to be able to support multiple unsafe compartments, then it's not enough to just say that this particular pointer is to some compartment. You also need to know which compartment it's in. This assignment might be a completely safe operation if the example and the data objects are in the same compartment. But if they aren't, then you've got a pointer that spans a compartment boundary, and this allows a compromise of one sandbox to then infect another. Even worse, you can't tell just by reading this code whether it's safe or not. This is one of the problems that we're exploring with Project Verona, a research language that we're using to explore these and other concepts. Each object in Verona is contained within a region, and regions themselves can contain arbitrary object graphs. Regions can then be arranged in trees with an owning pointer coming in from outside the region, and each tree of regions is then owned by a thing that we call a concurrent owner, or a cone for short. If you have a reference to a cone, then this doesn't let you access the cone's regions directly. It just allows you to asynchronously schedule some work that can later be done with access to that cone and all of the regions that it owns. This gives us not just type safety, but also concurrency safety, guaranteed deadlock freedom, and guaranteed data race freedom by construction. The region model in Verona provides us with a language-level abstraction that we can then use to expose unsafe compartments to a safe language programmer. Instances of unsafe libraries can be exposed as graphs of objects within a single Verona region, and CHERI provides us with fantastic tools for implementing this abstraction. We hope that this will let us build complex programs in a safe language without needing any kind of unsafe escape hatch, but still allowing us to reuse very large existing C and C++ libraries. So to sum everything up, CHERI lets us retrofit memory safety to C, which is the absolute minimum guarantee required to be able to stop bugs in C components from directly impacting arbitrary memory locations in the rest of a program. This in turn composes with stronger guarantees that you get from safe languages, allowing those safe languages to interoperate with unsafe code without sacrificing safety. And in future languages, this kind of safe composition should allow even stronger guarantees from those safe languages, letting them gracefully recover from failures of individual isolated instances of unsafe libraries.